Hello everyone, I would like to present and share my research on generative techniques in architecture and urban design, namely the Design Optimization Toolset or DOTS. It is packaged in the form of Rhino Grasshopper plugin and you can download it from the description below and use it. The video is introductory and please feel free to skip this video and move on to the next videos which have the software tutorials. Space allocation techniques are methods for solving general partitioning problems of 2 or 3 dimensional spaces and allocating program requirements to these subspaces. These problems appear in many architectural and urban design problems. It is a NP-complete problem and a general solution remains elusive due to spatial and combinatorial complexity. We present novel techniques to solve this general class of problems. We propose that to some extent, the geometry of architectural spaces can be generalized by formulating spaces along a curve and internal subdivision of the bounding curve. These methods for geometric formulation are subsequently integrated with optimization algorithms. The process of optimization refines the topological structure of a layout. It is based on well-known constraints of orientation, adjacency, proximity, circulation, area constraints, etc. In this paper, we describe geometric methods that generate commonly used shapes in design, and this includes rectangles, curves, general polygons, open curve segments, and composite shapes. Several features of an integrated framework are identified to evaluate process models and enhance their applicability in the development of architectural schemes. The features target various aspects of model manipulation concerning the generalization and optimization of solutions. They lead to the development of semi-automated design process, which is preferred in an artistic field such as architecture and urban design. The use of computational artifacts allows a designer to declare their intent in terms of geometric constraints and space allocation. This intent can be reviewed at a later time to understand the reasoning and the methodology that leads to an explicit design process. Applications at present include scales of floor plans, site feasibility studies, city blocks, as well as their geometric and topological variants. We have adapted reinforcement learning to propose a solution to the problem and used agent-environment interaction based on Markov decision process. The environment is a set of all possible locations, constraints, and evaluation mechanisms. Locations are internally represented as states and used as arrays. The agent is an algorithm that assigns space to each location. Action is the placement of space to a location. Reward is the numerical value assigned to the action taken by the agent. This is based on the constraints provided by the user. Learning is the mechanism that allows an agent to predict the value function without performing the actual action. So we have provided a standard routing example to illustrate the Q-learning algorithm. The space allocation problem is addressed by formulating a homeomorphic relation between geometric and topological requirements. As the area requirements are split, there must be a correspondence with the geometric form. The topological structure of the layout is used to generate variations. So, the subtree can be extracted and placed at a different node to generate the variations. Seamless transition between curves and polygons is achieved by using an algebraic expression of the curve. Architectural patterns can be generated procedurally to form spaces along a curve or off the medial axis or its transverse. Once discretized, the region can be operated upon by agent-environment interaction and allow topological optimization using reinforcement learning. In our approach, a space allocation problem is thought of as a set of tasks which can be mapped to computable models, or a design problem can be broken down into computable problems. These models call a set of methods from a common pool of SAT. or space allocation techniques. Then, by providing an integrated framework, the designer can combine models in various ways to generate unique solutions. We expose models to the user, which take the form of intuitive symbols. Each model is internally connected to a sequence of space allocation techniques. The designer may choose alternative models or solve the same problem. In this way, we provide a user-friendly, intuitive solution to the designer. These techniques are captured in the DOTS framework, which is developed as a user-friendly Rhino Grasshopper plugin. The designer may use numerous components to generate a sequence of solutions from the site plan to the building mass and floor plans at each level of the mass. Once the designer has selected the models and created a workflow, the inputs or constraints can be changed to dynamically generate the solution without any effort. We developed numerous functionalities for space allocation, including spaces along a circulation spine on one or both sides, along the periphery or internal partition of an enclosed boundary, or we can place a core and provide spaces surrounding it. There are specific problems such as site feasibility studies, which can be simply handled by a component. It was also possible to extend these methods with different kinds of constraints used in site planning, such as setbacks, stepbacks, maximum height, etc. We have included pathfinding and routing and attractor-based FAR distribution, along with allocation of grids and massing. In addition to these modules, there are a number of utility functions for geometry manipulation, data structures, and transport of data over the internet. We have tried to address the flexibility of design processes by introducing three techniques for semi-automation. The user may change the input step by step in an external Excel file, and the solver parses the inputs to generate the solution. The user may alter the geometry at runtime, or when there are many equivalent solutions, the user may choose to save and retrieve them. This leads to a highly flexible problem-solving experience. Design processes in architectural practices are flexible to the extent that constraints are changed continuously during the design process. To support this behavior, the scalability of the algorithm was developed. An application of space planning is illustrated here, which shows how to develop complex solutions. And once a DOTS workflow is developed, it can be applied to other geometries with constraints of that particular project. The workflow of components allows a reviewer to understand how the spaces are created and refer constraints used at a later time. This is the explicit design process. This slide illustrates the application of DOTS to develop a site feasibility study. It is an exact common problem that is typically used at the beginning of an architectural design project. So in this problem, a number of blocks have to be placed and a gross zoning has to be allocated to the floor plans. The zoning may take various forms, for instance, mixed use to retail, housing and offices, or a purely housing project may have various types of units to be placed on the floors. Further, various types of blocks may be used. Additional constraints may include proximities between the blocks or the proximities between functional requirements. Large-scale design problems can be formulated in other ways based on networks or graph theory. They rely on grouping of nodes, routing, and pathfinding. The problem formulation is based on cost functions for proximity, centrality, dispersal, and multiple connectivity requirements. Here we see samples where in the first solver, various types of nodes are placed and routes are determined. It is a proof of concept application to demonstrate grouping of nodes and avoid intersection between edges connecting a set of nodes. In the second solver, the footprints remain the same but FAR allocation responds to distance from the central path. That is the effect of FAR distribution of activities from points or curves. In the third solver, various types of parcels and building constraints are generated using tessellation algorithms and graph algorithms for centrality, dispersal, betweenness, etc. So they were developed as web applications, but the components are also provided in dots with more functionality. We have been able to integrate dots with other popular frameworks and exposed an API to the web developers. It has components to transmit geometry and data over the internet and connect to software such as DynamoRabbit or Rhino on a different computer. The data is an abstract object which contains various types of information such as geometry, type of space, connectivity with other spaces, and so on. By generating these objects, it is possible to provide a foundation for collaboration, such as energy analysis or daylighting, using other plugins. In this paper, we have attempted to provide a scalable solution to the space allocation problem, and we propose numerous features that will allow it to be extended to design applications. Novel techniques have been introduced to enhance the scope of computation in architecture and urban design. This led to the development of a framework of solutions which permits semi-automation and structuring a design process to show the intent and constraints. The proposal must be enhanced by introducing additional geometry modules for massing or partitioning. We would also like to address more types of design input and accommodate data from various sources such as IoT, spatial temporal data, origin destination studies, etc. Numerous programming languages and popular frameworks were used in developing the proof of concept. The project is open for collaboration and use. Numerous web applications are available and the plugin can be downloaded from GitHub. Thank you.